Welcome back. We are still working on inferential statistics. Previously in 9.1, we found estimating a population proportion. From sample data. We found from the sample, we found our point estimate. That we call p hat. And once we, and that is directly based on X over N. The people that match whatever the topic is over sample size. From there, we said the mean of the proportion equal p hat. And we said standard deviation for the proportion sampling distribution was the square root of p hat times 1 minus p hat over n. Now, those of you that were here for the last hour, we delved into that a lot more with one example for like the entire hour, like really dug into like seeing stuff. It's on the video. I should have it uploaded, if not tonight, sometime tomorrow. It's worth watching if you're like what the fuck is going on with this confidence interval shit. Go over it. We did stuff from 9.1. When we meet again on Tuesday, I'm going to do stuff from 9.2 to just reinforce that shit. So we'll have another video on Tuesday. 9.2, we are going to estimate a population mean. And we have to do it using sample data. Because we don't have information for the entire population. If we did, we wouldn't be estimating shit. We'd already have it. It'd be a done deal. So what we had previously for stuff, when we looked at this stuff in 8.2, in chapter 8, we said mu of the sampling distribution equaled mu of the population. But we don't have this now. But that's easy. We're just going to say the mean of the sampling distribution for means is X bar. This is our sample mean. We can calculate that if we've taken a sample. population or standard deviation. Standard deviation was the square root, or I'm sorry. I don't say this shit wrong. I'm pretty sure it was standard deviation of the population over the square root of n. Yeah, there it is. Standard deviation was the standard deviation of the population over the square root of n. We don't have that either. And it turns out that using S, which is sample standard deviation, isn't a good substitute. You guys ready? Anybody still writing? Okay, so there's this guy. His name is Gossett. This is the early 1900s. He's got a degree in chemistry and mathematics, and he's working for Guinness Brewery. Guess what? Alcohol is going to be part of the story of statistics in the worldwide. Now, we have found out that, like, if you have large sample groups, the larger the sample is, the closer you are to the law of large numbers kicks in, and you can use your S that we just got done saying was a bad or not necessarily a good substitute. You can use S for the standard deviation if you have n is really large, like really large. But what if n isn't really large? What if n is like 40 or 50 or some shit like that? What can you do? And so, like, he's working for this brewery and trying to, like, make sure, like, the best yield crops are used. So he's, like, doing samples of different, like, barleys that are produced in the fields and trying to find the right, like, bio strain, like doing some fucking genetic engineering, basically. Trying to, like, find the right crop to grow to, like, have the best stuff. And he goes through trial after trial after trial. And he ends up managing to find a way to do something that replaces or makes sure that we have a normal distribution for small samples. That's this guy right here. His name was Gossett. Gossett tried to publish, but Guinness wouldn't let him. His company wouldn't let him under his own name because it was their data under his name, his and their name. And apparently they didn't care if he used a pseudonym. So he used the pseudonym. Pseudonym is a fun word. Oops, already fucked it up. Pseudonym. That's fake name. If you don't know what a pseudonym is, the P is silent. He is the pseudonym student. And he called it the T distribution. And you know how our z-score was x bar minus mu over sigma? He didn't have sigma. So the t-score, sometimes capital T, sometimes lowercase t, is set up similarly, but on the bottom he has s divided by the square root of n. So like this bottom part simulates what we had before, with standard deviation equaled standard deviation of population over square root of n. Well, he's made his own distribution and he replaced sigma with s. And so the z-score is like the t-score, but an adapted standard deviation on bottom. You're not going to use this formula. Okay, this formula, the computer is going to do the formula for you. But because of this similarity and relationship to the z-score, a lot of ideal properties hold for the t distribution. And we'll write the list of properties in a second. Okay, looks like you guys are ready. T-score property, T-properties, T-distribution properties. And think Z-score. Z-score has the standard normal distribution. It's got a mean of 0 and a standard deviation of 1. It's like the best bell case scenario. Bell curve. So, like Z-score, it is symmetric and bell-shaped, centered at mu equals 0. The area on the left to the left of mu equals the area to the right, which equals 0.5. The total bell curve has an area of 1. You don't even want to see the formula they use to make that happen. That bell curve formula, the shape actually has a formula. There's a formula for it. It's an equation. Also, things that are similar, the tails approach the number line, but never actually touch it. That's a lot of good shit that matches up. Things that differ. It's a lot of matchup. I mean, it's got the same shape. It's got a mu equals 0. It's got the symmetry. The only thing that's different is the standard deviation is in 1. So let's explore that. One thing to note, T is different for different sample sizes. In fact, the only thing StatCrunch wants for the T calculator is degrees of freedom. And it says DF on the screen, and it's directly related to the sample size. It's n-1. Let me pause and let you all catch up. So how is T different? I'm going to show you a picture, and then we'll like visually see it. That way you can see it's a lot easier to see it and then write in words. Let's take a look here. You will find if you're going through this stuff throughout the semester, like you're looking for like things on confidence intervals and stuff like that, and you want to, and the hypothesis test, and you want to see workout examples. This document is filled with them, and you can find it in it's the file section. I'll show you. I'm going to reference it a lot, but I don't have time to do all the samples in it. But we will reference samples from it on occasion. What am I doing? Math. It's easier to read. All the math courses have the same stuff. Go to files and come down and look at Math 21 lecture notes. It's worth downloading. I'll show you, like, you'll see as I'm going through this stuff that there's actual, like, it shows the StatCrunch printouts. So you can do it yourself on your own in StatCrunch and make sure you match what the lecture notes say. And to make sure you can get better at StatCrunch, make sure you understand it. That's where this comes from. Let me find, there's my pretty graph that I want to use. So the blue one, the top one, is the standard normal distribution. That's our z-score. Mu equals 0, standard deviation equals 1. Now it's a little hard to tell because I used orange and fucking pink, which could kind of look the same when you got shading near them, so it wasn't that helpful. But the orange, that n equals 5, when the sample size was only 5, it's lower here. N equals 15 is higher, it's getting closer, and we'll see that as n gets large enough, the T distribution looks like the Z distribution. But you'll notice that all these curves kind of cross at the same, it's called the inflection point. It's one deviation out. And then after that, like the blue line is lower than the pink line, which is lower than the orange line. The area has to be equal 1 And if there's less area here in the middle, because it goes up shorter, they gotta make up for it being taller on the edges. So I'm gonna put that in words. The tails are, what are we on? E, this is E, this is E. E. Tails are longer for T. So like for the same standard deviation. S is greater than sigma, which makes the height taller for any given standard deviation. Which makes the height taller. I already said standard deviation above. It's a little bit above. Well, the height is greater. S height. And what's handy to know is that as n increases, the t distribution approaches the z distribution. And the curves look more and more similar. Those are the properties. I'll let you finish writing it, and then we'll talk about how they apply and what we do with them. So how do we use this? Well, if n is greater than or equal to 30, we are good to go. Use away. No restrictions. That's considered large enough. If n is less than 30, we require option 1. The population is known to be normally distributed. Or option 2. We have to do that what we did in chapter 4 with the QQ plot and box plot stuff. We got to make sure that the correlation coefficient R is greater than the critical value, CV. I'm sorry, absolute value R, I should say. Absolute value R. And we need to make sure that the box plot has no outliers. If any of those occur, we can use T distribution. That's all the boring jibber jabber that we got to talk about for what's going on. Now, like, how do I do it? We'll get to that right now. Cover StatCrunch, do some problems. Talk about 9.3. 9.3 is like, how do you identify between the difference between them? When you're doing homework, the homework's fucking clear as day. You know by the section number what you're doing, but in real life, that shit doesn't happen. No one comes along and says, hey, we need you to estimate the population proportion. You just given information what they're trying to find, and you need to deduce it. So how do we do that? That's what 9.3 is about. And it's a short talk. 9.3 is a short talk. Anyone need that longer? Okay, so practical like applications of this shit. Exactly what I said. Applications of this shit. One thing to note is they like to look at T alpha, which is kind of like Z alpha, and it's the area to the right of X under the curve. We'll do an example with that. Calculate T. This is our StatCrunch section. And start giving StatCrunch instructions. To calculate T, you're going to go stats, calculators, T. you need df degrees of freedom, which is n minus 1. Reset the questions I'm going to do here. And then to do for confidence intervals, or hypothesis tests, as we're going to start doing shortly. You're going to go stats, t-stats, then you have some options: 1 sample, 2 sample, or paired. I want to say we're going to do this in chapter 10. These two are in chapter 11. When we have more than 2 samples, that will be chapter 12 and 13. We don't have a whole lot of sections left. We got 10.1, 10.2, 10.3. No, 10.1, 10.2. I don't even know if there's a, yeah, there is a 10.3. 11.1 through 11.3. There's only 2 sections in chapter 12 and 1 section in chapter 13. So things are going to get slower here. You're going to have time. We're going to talk about a project either next week or the week after, the beginning of the week after. And you guys will have time to work on the project and stuff like that. You'll see, it's not too bad. Most people, well, after they're done bitching and complaining about having to do a project and they actually start, they're like, this isn't too bad. This is actually kind of interesting. I know, I bitched and complained about it when I was a student. Let's see. Oh, what will they ask you? You either have to have with data, which means individual responses, of course. Or you need, this is what you're more than likely going to have, with summary, you need sample mean, X bar, sample standard deviation, S, and sample size, N. And why don't we take our break here before we start diving? I don't want to, like, we can stop halfway through or one problem in, but I think here's a good spot for a break. Clear your head for a little bit. All right, something that was asked while we had the video not running. Are we not using this t-stats 1 sample thing in chapter 9? We are. The chapter 10 and chapter 11 stuff was referring to hypothesis testing. And we're going to be using stats, t-stats, one sample for confidence intervals today. Let's go over and take a look at StatCrunch. So this is the section 9.2 homework. I did 3 of them with students earlier. Hit you guys with 3 of them now. I will be covering more of these on Tuesday in the Math 321 class. So like, try to do the homework without watching them is a better way to go. See what you understand and then go from there. All right. So I'm going to do this. Let's say get more help, get my StatCrunch window ready. I know I'm going to need it. I always need it. Okay, so problem 1 says determine the t-value in each case. And it'll tell you to click on the table. This is the way you used to do it. This table was always about the area to the right of the curve. And if you wanted anything on the left, you had to use symmetry. And fuck all that. We have technology now. So we want to find the t-value such that the area in the right tail is 0.25 with 9 degrees of freedom. So I'm going to write this down while I'm showing you guys. We're going to stats. Stats, calculators, T. Notice that right now the area that's shaded is to the left. If I change this inequality symbol, it shades it to the right. So you just address the inequality symbol to change which side you're shading. Simple as that. We want, it says area in the right tail. So we want on the right side. And it says find the t-value. So we're looking for t. So that the right area is 0.25. This is the area stuff. And it says with 9 degrees of freedom. Your results will vary. You know, this is a fucking T calculator. I don't know why they couldn't program this in to say fucking T. It says T at the top. All they had to do is fucking put T here. Rat bastards. They didn't though. To 3 decimal places, that's what I get. I need to round up to 0.703. And there's parts A through D on this one. They don't tell you that. I was bitching in a storm up today in fucking morning class going and thinking I'm done with the problem. Nope, there's more. And it's worth going over with you. Problem B is very much the same thing as problem A. They want you to change the area in the right tail and they want you to change the degrees of freedom. So I'm going to put the degrees of freedom at 15. And I'm going to change that area in the right tail to match what they requested. 0.005. I can see it's the right tail. It's not a very big sliver, but it's red there. And they give me that. 2.946, and I'm going to need to round up to 2.947. So maybe for your lecture notes, the screen has, for part A and B, well, they're all kind of here. It says standard. Yeah, standard. It says between. There's a picture of a curve. There is a DF box. There is probability that X, then a box here for symbols, a box here for your amount equals a third box. If this symbol right here is greater than, it shades to the right. And if it's less than, it shades to the left. So it kind of points in the area, the direction that's being shaded. Points to shading direction. Parts A and B, we use standard. We leave it on standard tab. Fill in DF. And that box. Along with choosing the right inequality symbol. Then I'll tell you, I'll write down what C says and tell you what you're gonna do about that. Part C says area to the left. And it will give you an amount. Mine says 0.01 and it tells me degrees of freedom is 26. Then it says hint, use symmetry. It's got it. This is exactly how it shows it. Hint, use symmetry. It's in brackets. This shit is for the table. I mean, we could use it on this up here and never have to change the graph. But I think it's easier to make the inequality change in the right direction. Just choose X less than, and you're good to go. Thank you. Good, Angel? Yeah. So I plugged that in and I put the degrees of freedom as 26. I changed my t-value. I changed my inequality. Notice it says negative 2.479 basically. What that symmetry thing was saying was, watch how this value here changes if I change the inequality. And I put that back at 0.01. Oops. This was the value, now it's this value. The symmetry is when you do it on the left and you use the same value, It's just a negative. That's what they meant by it. But I figure if you just change the inequality, you're better off. You're good to go. So I put it in. I'm going to click check answer. And then it says find a critical value that corresponds to 90% confidence. Assume 10 degrees of freedom. So let's talk about that for a second. And the justification behind what we're doing here. Part D, 9.2, number 1, part D. Find T for 90% confidence interval. CI. Assume DF equals 10. On a bell curve, the confidence intervals usually indicate middle regions. Confidence interval. Confidence intervals give you the numbers on the end. Where this corresponds to what we need is we need to use the between tab. And we'll plug in the information that they ask. The 90% confidence means 90% area. Which means that right box will be 0.9 for me. I know that value changes because it was different this morning. I'll click on between. I'll change my degrees of freedom to 10. I'll change my box on the right to be 0.9. And you'll see that you get the negative value and the positive value of the same number. They want you to use the positive value and make sure you round to 3 decimal places. They caught me earlier. I fucking didn't round. I saw 4 decimal places. I figured just plug it in and nope. So they only asked for one of them. You use the positive one. Okay. Any questions on that?
Your degrees of freedom always the difference between.
It's n minus 1, always. So for this 10 degrees of freedom, the sample size was 11. Because 11 minus 1 gives you 10.
Yes.
Problem number 2 says the data from a simple random sample with 25 observations was used to construct the given probability plot. It looks like they give us a graph. I'm going to start jotting down some notes over here. But I think you might want to see the graph before I transfer over to it. It was used to construct the plots given below. The normal probability plot that was constructed has a correlation coefficient of 0.952. That sounds important. That's my R. Judge whether a T interval can be used. Can we use a T distribution? Let's take a look at the graphs. Well, this doesn't tell me a whole lot. There's dots outside of it. That's usually not a good sign. We have an outlier on the box plot. So I'm going to make a note of that. Box plot has outlier. And let's see, they gave us the table of critical values. It said N was 25. So we're gonna need the critical value 25 probably. The CV for 25 is 0.959. All right. I wrote down the shit from the stuff they gave us. Let's come over to the document camera to talk about it. Recall to use this. Option A is N is greater than or equal to 30. They gave us N equal 25. So fail on this now. Option B was for N less than 30, we had some requirements. One was to be normally distributed. And there was no information on that. So that's a fail. Option 2, which requires a little more room to write, we need to compare the critical value versus CV. Is that true? And does the box plot have outliers? Or better yet, have no outliers. That's what we need for true. So all that chapter 4 shit I told you that I wasn't going to test you on, and you're not going to have to calculate this shit on the final exam, but it does come up later on in this stuff. Like when can we use T? Well, my R value was 0.952 and my critical value was 0.959. My R is less than my critical value, so I failed that one, and that's usually enough. But we also failed the box plot thing. We can't use T for those reasons. That's what the homework's going to ask you to put. It's going to be one of those fucking sentences that has like a couple drop down boxes and a bunch of blank fields. And you're like, you got to go through it slowly to figure out what the hell they're asking. But we're trying to say this stuff. And we need to see how, like, what boxes to click to make that work. All right. So let's come over here and answer that stuff. It says the normal probability plot, blank the data could come from a normal population. And the options are does not suggest or suggests. So let's see, the normal probability suggests the data could come from a normal population. It doesn't say anything about that. And our results, like our RCV, doesn't show that. So this is a does not suggest. Then it says because 0.952, there's a greater than less than thing. This looks like this is where they want me to put the R and the CV stuff. The CV was 959. And then it says, and the box plot blank outliers. It had outliers. Yeah, shows. We want to say the box plot shows outliers. So a T interval shouldn't be or couldn't be constructed. Okay. We're not gonna do number 3. We're gonna come down to number 7. Because this one trips up a lot of students. Number 7 says, in a survey conducted by the Gallup organization, a renowned polling company, survey company, it said they surveyed 1,100 Americans. So N equals 1,100 adult Americans. And they were asked how many hours they worked in the previous week. So this is hours per week question. It said on a 95% confidence interval, the lower bound was 42.7 and the upper bound was 44.5. This must be talking about hours, because that's what they were asking about. Provide 2 recommendations for decreasing the margin of error. 2 ways to decrease the margin of error. Those that were here for Math 321 saw this. I did this with them already. We're gonna do it again. So let's come over here and draw a picture of what's going on. We got our mean in the middle. 95% covers up a big chunk. They've got the lower bound right here is 42.7 hours. And the upper bound here is 44.5 hours. This doesn't seem realistic. The average person works over 40 hours a week. I'm not buying it. I mean, there are a lot of people with 2 jobs. Maybe the people that were like salaried people, it's not a lot of them gonna have to work more than 40 hours. I guess maybe it's possible. You get a high salary, but you're there until the job's done on a salary, whether it's 10 hours or 80 hours. You gotta get the job done. You're paid to do the job. So what is the margin of error? This is our mean in the middle. We could calculate this by doing 42.7 plus 44.5 divided by 2. That would give us our mean in the middle. And it looks like it's 43.6. The margin of error is this distance right here. That's E, and that's E. Now, one of these is easy if you understand what confidence interval means, what the percentage means. The 95% means area under the curve. Curve is 0.95. %, would push it out further because it has to have more area. more width to get that 0.99. Which means increasing your confidence, level of confidence is bad. Increasing level of confidence raises error. Conversely, decreasing lowers it. So if you understand that principle, that's one of them. And you will understand it soon enough. If you don't now, you will. You'll get it. We're hitting on it so damn much this for the rest of the semester. It's gonna happen. You'll get it. And then I'll click back over and show you what the other options are, because like they'll kind of lead you into how you can figure this out. So second way. Let's see question. You guys ready to see the question? Let's do it. Angel?
Yeah.
Good.
Thank you.
Okay, so we said decrease the confidence level. Let's think about the other ways. Decrease the standard deviation of hours worked. The standard deviation is something we calculate. It's based off the data. Is that something we really have control over? We don't have any control over that, do we? The only way we can, because that's like how different the numbers are. The only way we can like affect this is go, well, if you work less than 40 hours a week, fuck off. We're only asking for you, we don't want your answers. And then it's not like a realistic survey, it's not a valid survey. So there's no real way to affect the standard deviation by just doing it, like maybe waving a magic wand. Increase the confidence level is out. That was D. A is out. B says decrease the sample size. C says use fewer degrees of freedom. Those kind of mean the same thing. Because the D degrees of freedom is n minus 1. So if the degrees of freedom go down, the sample size is going down. So I already know I got one way. This looks suspicious, because if one's right, the other's right. And then I'd have 3 ways, but not they want us to click 2. So I'm thinking maybe increase the sample size, but I don't know. But if you don't know, like, don't just fucking give up, experiment. We can experiment. Let's see. We want to see whether increasing the sample size will affect shit. Let's come over here and let's make a, let's do this stats, T-stats, 1 sample with summary. I calculated the sample mean myself. It was 43.6. And the sample size was 1100. I don't know what sample standard deviation they had, but I don't know, let's try, I don't know, 15. Let's see what happens. Confidence interval was 95%. So, oh shit, this is pretty close. 42.7 and 44.5. Fuck. That's pretty close. They've got 42.7, 44.5 to 1 decimal place, 42.7, 44.5. So, like, let's check. And even if I didn't have that, even if you guess like a lower standard deviation, which is fine, you can still test the idea with any numbers here. We can go with 100, and I can go with 3, or let's go with 5. And it gives us a 99.7 to 100.3. Then just try the same thing. I had 105. I'm going to make a new window that has T-stats, 1 sample with summary. I'm going to do the 105 again. But now I'll lower the sample size down to 100. Let's see if decreasing the sample size affects it. I didn't change the confidence interval. So this has a lower limit of 99 and an upper limit of 101. Those are 2 apart. The one I started with the higher number sample size was 99.7 to 100.3, which is only 0.6 apart. It sounds like lowering the sample size made it bigger. But we can toy with it. Let's make this like, I don't know, 5,000. That's bigger than 1,100. And now we got 99.86 versus 100.13. Do I still have the thing where I had that over here? Maybe. Oh, I edited it. Never mind. I'll just use these. So I'm going to shift over to the thing and like discuss what this showed. So we experimented. We can experiment. Figure this out. The responses suggested sample size is an option. Affects it. Those were the only 3 other options. They were all related to sample size. There. So go to stats, T-stats, 1 sample with summary. You need sample mean, X bar, standard deviation, S, and size, N. So pick 2 values for these. I used 100 and 0.5. Not 0.5, 5. That's what I said. Then pick 3 numbers for these that are very far apart. I did n equals 100, n equals 1,100, And we did n equals 5,000. So let's see. Here we had the mean is 100 in the middle. And let's just call that 99 and this 101. So that's like 100.5, 99.5. The n equals 1100, I'll do in green. It said 99.7 to 100.3, which is like right here to right here. My error is that size. That's my middle size. When I said n equaled 5,000, we got 99.9 or 86 to 100.14. 99.86 is pretty fucking close to 100. So this is what we got for n equals 5,000. And the error has gone down. I think seeing it on a number line makes it a little bit clearer rather than just experimenting. And when we did n equals 100, it was all the way out to 99 and 101. That was n equals 100. So the margin of error on that one, look at that. That's fucking a really long E. So it looks like increasing n decreases error or margin of error. I didn't go to the formulas. I could have gone to the formulas and did some math jargon with you that most of you would have said, that's not fucking helpful. Or I could show you how to use the tools you have available to you to experiment and figure shit out on your own. A lot of learning in college is actually self-learning. Every time you do homework, you're figuring shit out on your own. Right? Use the tools you got to experiment. That's what we did here. I'm going to add this. None of these questions so far have asked for a statement of confidence. So I'm going to write a statement of confidence for this last question we did. But I'll let you guys finish writing that. You guys ready? Okay, so we had, I'm going to put that data back up, the sentence that we started with that gave us information about this. It said n equaled 1100. So we're going to write a statement of confidence for 9.2, number 7. We have a 95% confidence interval, so we are going to say we are 95% confident that the true or that the mean number, well, now we got to reference what the problem was about, number of hours worked per week by an adult American. That was what our sample group was about. is between 42.7 hours and 44.5 hours. And I just pulled it from the information. As we go through these tests and hypothesis tests throughout the semester, I'll keep doing this, showing you how to pull the information, write a statement of confidence, along with doing the hypothesis intervals when we do those as well. I'll even show you the connection between confidence intervals and hypothesis tests, but we gotta do the hypothesis test first. All right, so let's take a look at 9.3 real quickly. 9.3 doesn't tell you portion or mean. So we need to read the problem. And pick out information that will guide us to a proportion test, or will guide us towards prop stats or t-stats. Page. Anybody else need it up longer? Angel's usually my barometer here. So let's start discussing it. So if they give us stuff that looks like a qualitative data, or two outcomes that a person chooses between. Like if they were asked yes, no questions. Are you male, female? Are you a Republican, Democrat? Shit like that. Any situation where part of the population matches the research topic. And the rest doesn't. It's a little bright. This is gonna be a proportion problem. This happens in real life. You're like, I don't know what we're doing. It changes what formulas you use. It changes how you calculate it. So it's important to be able to recognize between them. If they give us quantitative data, you know, like numbers and shit. We might have a table of numbers, table or column of numbers. There's really only a couple ways they can give it to us. They got to give us the actual number, or they got to gives a summary that will say mean equals so-and-so and standard deviation equals so-and-so, some number. They might say X bar and S, but unlikely. They might just say mean. It might say mean in the problem. If it says mean in the problem or proportion in the problem, it's a dead giveaway. Mean uses t-stats. And then for both, in real life, make sure the requirements are met. We talked about the requirements already. And do the same only if the homework asks. It's if they don't ask about it, you can usually assume that they are met. And with that, you can get the fuck out. If you like, GTFO. I am gonna do sample problems from 9.3 in Math 321 from 3 to 4, is it 4 to 5? What, I don't know when the fuck we meet. 4 to 5 on Tuesday. The hour before this starts, it will be in a video available. If you wanna come take a look at it, I mean, like on Wednesday or so. Next week, you'll be able to see examples from 9.3. And maybe 9.2. But we already did 3 examples in here for 9.2. I can only do so much of your homework before it's like, why am I even assigning homework? You know what I mean? Have a good weekend. I'll be at the Starbucks at Turner Tahoe Joe's from 8 to 10 on Sunday morning. If you're interested, let me know, email me.
Put it changes in, it's like just looking at how to find the probability.
Reading question. Sure, I'm reading the question, give me a second. An exit poll of 300 voters finds that 144 voted for the referendum. How likely are the results of your sample? The population reporters, voters in the town of the referendum is 0.51.
Is there, I feel like I just blank out sometimes and like, I don't even know what they're asking.
Was it 144 out of 300?
Yeah, 1.4.
So we can find that proportion here, and that's 0.48. Fewer than 144.
Good night, guys. Thank you.
Good night.
Good night. Really? Log in here, go fuck yourself. Calculator is normal. We're assuming it's a normal population. It's people.
Yeah.
And so. They didn't give us a standard deviation.
Yeah, that's why it's like, that's why I blank out when it's like, oh.
Okay, so you have to go and calculate the mean and standard deviation. The meaning is the same thing as the 0.51.
Okay.
Then you have to do the. Let's work it out. Square root of p times 1 minus p over n. Well, my sample group had 0.48. Do they want us to use that? Let me read the wording again. It's very, it's a little bitchy of a problem, isn't it?
Yeah.
So they're saying it's in general it's 0.51. Let's try with 0.51 and see what happens. Since that's what I'm using. It was 300, right?
Yeah.
Zero. Two, 886. 739. And we're gonna say probability is. Less than what?
Sorry.
It says fewer than 144, doesn't it?
Yeah, it just says zero.
Okay, so the 144 was 0.48. So we're gonna say 0.48 there.
Oh,
and
yeah.
we get 0.1493.
Yeah, that's it.
Is it? Okay. Which is greater than 5%. This is 14.9%. If it's under 5%, it's unusual.
Okay, so basically just get the proportion of everything and get this regular this one.
Yeah,
Just, okay, that's.
then I need stats, you can take this page with you.
Oh, actually, I don't know if I could keep you any longer, but I had it like 2 more. Actually.
Why don't you send me, ask my instructor, so I can like respond, rather than me trying to read on this fucking tiny ass phone.
I had it like up there, like before class, I was doing it, I was like, okay, let me take, it was just that part, that small part.
Sample, shape of the distribution of the time required to get an oil change. Record, however, records indicate the mean time is 16.5. Suppose the manager. There we go, okay. Suppose the manager agrees to pay each employee a $50 bonus to meet a certain goal. On a typical Saturday, the oil change facility will perform 45 oil changes between 10 a.m. and 12. Treating this as a random sample, that's my N. There would be a 10% chance of being at or below what value? Okay, so
It tells you the standard deviation.
yeah, the mean is 16.5. Oh, that's my X bar. And my standard deviation is 4.8. Okay, so 16.5, still a normal calculator. 4.8. And we want below 10%, so we're gonna say below 0.1. Which is different than what they have. Oh, I know why. Because when you're doing these, this is the population standard deviation. We need to use the standard deviation of the population divided by square root of n. So I gotta do 4.8 divided by square root of 45.
Okay.
That's what's off. And what was I doing? 0.1 over here, right?
Yeah.
15.6.
Yeah, I had that, but I was like, I got 15.9, and I was like, what? When I got it wrong, I think I might have just messed up somewhere else.
If you rounded this, like if you said 0.72 and 0.1, it changes this somehow. So this is still 15.6.
Yeah, I think I just messed up somewhere else.
Yeah, you might have, I don't know. Probably somewhere in this calculation.
Yeah, probably there. I use the phone calculator, and I'm like, oh, sometimes I might press the equal signs like twice.
Right.
Yeah.
You want this?
Yeah. Thank you.
Huh? What's the third one? You said you had another one. If
Oh,
it's
yeah.
quick, I'll go over it. That ain't fucking quick. It's a whole goddamn block.
No, that's one problem.
Okay. According to a survey in a country, 19% of adults do not own a credit card. Suppose a random sample of 300 adults is selected. Would it be unusual for a random sample of 300 adults to result in 42 or fewer who do not own a credit card? So we're using mean is p hat, which is the, does it say it right? Not own. Didn't I go over this fucking question in class?
I wasn't in here. Oh, I wasn't in here.
Watch the goddamn videos.
Oh,
I know I went over this in class. Pretty sure I did. But. Let's see. We had a sample of 300. So you need to do. Find your standard, so the mean is the P, which
Yeah.
is 0.19.
mhm.
You need your standard deviation is 0.19.
0.19, then -1.
Yeah, and then divided by 300.
Yeah,
Take the square root.
yeah, I got that far.
Okay. So let's see what that is. 0.19 times 0.81 divided by 300. Take the square root. And I get 0.022649,503. To result in 42 or fewer people. This is in terms of proportions, so we need to know what 42 out of 300 is. 0.14.
Oh, so then do you do between or?
No,
No.
I'm gonna put 0.14 here. All of this is based on proportion, so the 44 people doesn't help. The proportion that they are of the 300 is what we
Oh.
need. Does that make sense?
Yeah,
And I don't know if it had a response,
yeah, that's,
and you can see the 0.0136 is right there. So you just gotta use the formulas.
Okay.
I don't know, let me see. At the fucking bare minimum, do this. If you don't wanna watch the whole videos. I get it, it's 2 hours. Usually 2 hours. Come in and go. All right, I'm recording them. So let's go look at the fucking paperwork. This is what I scan what I write. It's in the modules you can see. And come down and look at samples that I've done.
no way.
So I did problem 1.
I got it, so,
I didn't do problem 6 or problem 2.
but still, like, even those. That is helpful.
Yeah, so just go to the modules. You can tell the difference between them. The paperclip is the scanned version, the chain is the link to the YouTube video.
Okay. Alright, thank you, Jones.
Uh-huh.
Sorry for giving you a little.
It's okay, I'd rather, that's my job, I'm here to help. Definitely watch the videos, though, if you've got time. I mean, you're supposed to be attending class, like, that's the point of the lecture.
Yeah, no, I
You're just winging it is what you're doing.
No, I just gonna attend that one time. That was it. Because my mom was in the hospital.
How's she doing?
Sorry?
How is she doing now?
She's doing a lot better, she's back home.
Good.
Thank you, Jones.
Uh-huh, have a good weekend.
You too.